This video introduces the project VoxPoser, Composable 3D value maps for robotic manipulation with language models. How can we enable robots to perform manipulation tasks with an open set of language instructions and an open set of objects? And can this even be achieved in a zero-shot manner? To tackle this, prior works typically map the language instructions to robot actions by learning unlabeled demonstration data. However, this data are hard to obtain and thus often generalize poorly to new instructions aside from even new behaviors. Instead, we propose to leverage large language models and visual language models that have rich open-world knowledge. By using a code interface and without any additional training, we can directly use these models to label 3D affordances and constraints in the perceptual space of the robot, which we refer to as 3D value maps. After obtaining the 3D value maps, a motion planner is used to generate the robot actions. Now we show an example of extracting affordances for the instruction "Open the top drawer." First, the language model generates code to initialize an empty voxel map over the robot workspace. Then, it invokes the visual language model to identify the relevant objects or parts for the task. In this case, the two drawer handles are detected, and the top drawer handle is selected by the language model. Finally, the language model assigns an affordance value to the voxel of the top drawer handle. We also apply smoothing operations to propagate the values to the full workspace. In addition to labeling affordances, VoxPoser can also label constraints in the scene for instructions such as "Watch out for that vase." Similarly, an empty voxel map is initialized. The vase is detected using the visual language model, and its occupying voxels are being assigned a low value. Finally, all constraint maps and affordance maps are composed together to form the final value map. Based on the task requirements, the language model and the visual language model can also synthesize rotation maps, gripper maps, and velocity maps. These maps are then used jointly by a motion planner to plan an SE3 end-effector trajectory with gripper actions. Finally, an operational space controller is employed to follow the trajectory to grasp the top handle. After that, new value maps are synthesized to enable the robot to open the drawer. We now show the videos of VoxPoser performing manipulation tasks in the wild. We would like to note that all trajectories are zero-shot synthesized. VoxPoser can perform articulated object manipulation, including close the top drawer, turn on the lamp, and turn open the vitamin bottle. In addition, it can perform elementary deformable manipulation, including take out a napkin, sweep trash into the dustpan, and hang the towel onto the rack. Lastly, it can also perform many other everyday manipulation tasks, including take out the bread from the toaster and lay it flat on the board, set a table for my pasta, and measure the weight of the apple. Because the language model output stays the same throughout the task, we can cache its output and re-evaluate the generated code using closed-loop visual feedback, which enables fast replanning using MPC. This enables VoxPoser to be robust to online disturbances to handle tasks such as sort the paper trash into the blue tray, while the object poses are being disturbed, and the trash is being manually taken out of the tray after the robot has put it in. And also, close the top drawer. After the robot closes the drawer, it was opened again by the user, and its pose is also changed. We also observe several interesting emergent behavioral capabilities derived from the large language model. Given the question, which block is heavier, VoxPoser can come up with strategies to push block off the ramp and measure their traveling distance. The block traveling the furthest is concluded to be the heaviest block. During the execution of the task, set a table for my pasta, User can give further instructions such as "I'm left-handed," which requires the robot to reason its behaviors using common sense and place the spoon on the left side. For tasks that require high precision, VoxPoser can also take in fine-grained language corrections such as "you're off by 1 centimeter to the left," which allows the user to verbally control the precise movement of the robot. Finally, given a task with insufficient information, such as open the drawer precisely by half, but the object model is not available, VoxPoser can come up with this multi-step visual program to first fully open the drawer, record its displacement, and close the drawer precisely by half. For more information, please see the website voxposer.github.io. Thanks for watching.